When an autonomous coding agent delivers a working script that meets your constraints, standard engineering practice records a success. The assumption is straightforward. The model read the instructions, and it followed them. Take a strict rule, like requiring a prefix on new Git branches. The agent creates it, and the evaluation logs a pass. But if we rewind, delete the rule entirely, and run the task again, we often see the exact same output. The agent didn't prefix the branch because you commanded it to. It prefixed the branch because its pre-trained default behavior naturally aligned with that format. The green checkmark isn't measuring compliance. It is measuring coincidence. Relying on aggregate task success to evaluate models hides this distinction. It makes it impossible to know if an agent is actually obeying the operational constraints of your system or simply executing defaults that happen to pass the test. Standard instruction following benchmarks attempt to solve this by loading every constraint into a single user turn and measuring the direct response. Standard coding agent benchmarks go the opposite direction. They allow multi-step workflows, but collapse the entire trajectory into a single binary metric. Did the final code compile and pass the tests? Neither of these methods reflects a production environment. Deployed agents don't receive instructions in a single block of text, and they don't operate without generating dozens of intermediate artifacts along the way. A new measurement protocol called harness-IF addresses this structural gap. Instead of grading the final output of a task, it isolates and evaluates individual rules across the entire context window. To measure genuine agent compliance, we have to stop scoring the artifact and start scoring the operational rules along the trajectory. A production agent reads a multi-authored stack of instructions, a harness default, system prompt, tool and skill descriptions, project files, and the user's request. Written by different parties, they form the operational contract the agent must uphold. The exact same formatting requirement can be followed or ignored, depending purely on which of these 6 surfaces carries it. Harness-IF will test this by extracting 642 atomic constraints from real-world project files and placing them across the different surfaces. A single task trajectory runs through the stack, then shatters into a wide grid of pass or fail evaluation cells. Scaling this across 12 frontier models yields over 40,000 rule-level verdicts. By scoring rules individually across these surfaces, we map where a model drops a specific instruction rather than settling for a generic task-failed notification. We still have the problem of coincidence. Passing a rule that perfectly matches a model's default behavior tells us nothing about actual compliance. To map unprompted defaults, harness-IF uses a zero-injection probe. It isolates a target rule, removes it from the prompt stack, and runs the exact task across 9 parallel builds. If at least 5 of those 9 builds naturally satisfy the missing rule, the behavior is labeled a line prior. If they violate it, the default behavior stands in opposition, labeled against prior. This stratification allows for a new metric, against prior accuracy, or APAC. It calculates compliance exclusively on the against prior slice, scoring the agent only on instructions that actively push against its natural tendencies. Because APAC is computed on the exact same pool of eligible verdicts as standard accuracy, the numerical gap between them provides a direct, like-for-like measurement of performance inflation. APAC strips away the coincidental successes. It isolates instructions where the model actually has to read, process, and obey a rule it would otherwise ignore. Standard accuracy places 12 frontier models high on the axis, ranging between 72 and 86%. But under the against prior baseline, every score drops to between 66 and 79%, revealing a performance gap of 3.6 to 7.4 points. This inflation isn't a uniform penalty. The gap varies twofold across the cohort. Standard aggregate scores actively misrank models by a margin specific to each model's underlying architecture. Evaluating coding agents without an against prior baseline results in inflated metrics and compromised architectural decisions. Beyond measuring baseline compliance, we have to determine how an agent resolves contradictory instructions placed in different layers of the context stack. The prevailing engineering assumption is based on prompt depth. Recency is expected to dictate precedence, meaning the final user instruction should consistently override earlier constraints. A counterbalanced pilot forces mutually exclusive rules onto opposite surfaces to visualize the actual hierarchy of precedence. System prompts, project files, and user instructions share a 3-way tie for first place. tool descriptions land in fourth, and skill descriptions in fifth. The final user turn does not dominate the stack, it merely ties for first, while instructions embedded in tools and skills actively lose conflicts. Precedence does not scale with recency. Placing critical operational guardrails deep inside tool descriptions leaves them highly vulnerable to being overwritten by adjacent surfaces. This breakdown categorizes the anatomy of the 8,440 compliance failures recorded in the benchmark. Over 77% of failures are classified as shortfalls, compared to just 20.8% for oversteps. The overwhelming majority of compliance failures are omissions. The agent simply falls short of executing a demanded action, rather than generating a hallucination or outputting excess code. This exposes a major structural flaw in how we audit agents. Verification layers tuned primarily to catch excess output address only about a fifth of the problem, leaving them entirely blind to the other 80% of failures, where the agent simply fails to act. Segmenting by rule type isolates the problem further. Output control is the single weakest compliance family, scoring the lowest pass rate across 11 of the 12 frontier builds at roughly 70%. Rules demanding specific, rigid departures from a model's default syntax are the most likely to break. Output control represents the densest concentration of failures, making it the most productive target for immediate remediation. Validating these metrics requires acknowledging the honest limits of the Harness IF instrument. Nearly 87% of these rule-level verdicts rely on an LLM judge. Under a judge swap reliability test, agreement drops to a kappa of 0.163. When we apply confidence intervals to the ranking, the neighboring models begin to statistically overlap. The absolute percentage scores are heavily tied to the specific judge instrument evaluating the code. They cannot be treated as a universal ground truth for a given model. However, the broader cross-model patterns, the heavy weighting of omission failures, the weakness in output control, and the consistent against prior gap hold firmly across the data. For engineers building autonomous systems, the directives are clear. Preserve the provenance of your rules. Grade specific rule opportunities, not just overall task success. And always counterbalance your instruction surfaces before testing which prompt layer takes priority. True agent compliance operates at the execution layer. Until you isolate your against prior baseline, you are optimizing for an illusion.